Hello everyone. Today we are going to discuss the chapter Thermodynamics. Okay. So let us start with some common terms used in thermodynamics. Number one, system, and number two, surroundings. Number three, boundary. Okay, let us first learn these terms. System. What is system? In thermodynamics, the part of the universe which is under consideration is called system. For example, suppose we are concerned with a beaker containing water. We are boiling the water and observing the boiling water. So for that particular experiment, the beaker with the boiling water will be considered as the system of the thermodynamics. And surroundings, then the rest part of the universe will be called surroundings. The rest part of the universe means the beaker with the boiling water will be system, and whatever be present in the rest of the universe will be called surroundings. Practically, the things which are very far from the system does not have any significant effect on the system. Therefore, as surrounding, we consider the atmosphere present surrounding the system, or whatever the objects are present surrounding the system is called the surrounding. Okay, and boundary. Boundary is the imaginary wall between the system and the surroundings. Now, suppose the water is containing, the beaker is containing the water we are boiling, or the reaction we are conducting inside the beaker. So we are concerned only about the reaction mixture or the boiling water. We are not considering the beaker. In that case, the wall of the beaker will be the boundary, because the wall of the beaker is separating the system from the surroundings. But sometimes it can be imaginary also. Imaginary means the boundary will not be made up of any matter. Okay, for example, suppose the whole beaker with the solution or with the boiling water is the system. Then the surrounding will be the atmosphere present surrounding the beaker. So we have to imagine there is an invisible boundary between the outer wall of the beaker and the atmosphere present surrounding the beaker. In that case, the boundary will be imaginary, hypothetical boundary. Now let us go with this term system. What is system? Since we will mainly deal with the system, we have to first understand, depending on the nature of the boundary, system can be classified into different types. Okay, mainly there are three types of system. One is open system. What does it mean? Open system. Open system means, just now we have taken the example of a beaker containing boiling water. So when we are heating the water is getting evaporated and the water vapor is mixing with the atmosphere. Now observe two things here. One is the heat is supplied from outside and entering into the beaker. So the system is exchanging the heat or any kind of energy with the surroundings. Okay, let us draw a diagram to understand it. Suppose this is our system and we are heating it with the help of a burner. Okay, now water is getting evaporated. So this system is absorbing the heat from the burner. It means the system can exchange energy with the surroundings. Number one. Number two, since the water is getting evaporated and mixing with the atmosphere, it means the system is exchanging matter also with the surroundings. So this type of system where the system can exchange both the heat, both the energy, any type of energy, and the matter with the surroundings is called open system. Okay. Second type is closed system. Okay. Now consider the same beaker but in closed condition. The beaker is closed, covered, and we are performing a chemical reaction inside the beaker. Suppose AgCl is present, NO3 is present and HCl is present. They are reacting to give AgCl, for example, and suppose we are heating it. Okay, or suppose the dry calcium carbonate is there, we are heating it and the calcium carbonate is converting into calcium oxide and carbon dioxide in small quantity, but it is closed. The carbon dioxide which will be evolved, we are not allowing the carbon dioxide to come out and mixing with the atmosphere or with the surroundings. So in this case, the system is exchanging the energy with the surroundings, means the system is absorbing energy, but it is not exchanging the matter with the surroundings. So this type of system is called closed system, where the system can exchange energy with the surroundings but not the matter. Okay, and third type is isolated system. Isolated system. Now, in case of isolated system, the system neither can exchange the energy nor the matter with the surroundings. Let us consider one thermoflask. So, if we keep hot water inside the thermoflask, if we close the cap, now see, the hot water will remain hot for long time. It means what? The heat which is extra heat in compared to the surroundings present inside the flask is not coming out easily and mixing with the atmosphere. And since the cap is closed, so water vapor is also not coming. So this type of system is called isolated system, which is neither sharing the energy nor matter with the surroundings. But practically 100% isolated system, making of 100% isolated system is very difficult. Therefore, this type of thermoflask or insulated beaker can be considered as isolated system, because to some extent it works as an isolated system. Okay. Now, next is state of a system. What does it mean? State of a system. State of a system. Now, if a system is there in equilibrium condition, its volume, these terms like pressure, volume, temperature, and the composition or the quantity, we consider it as number of moles. These are fixed. So that will be called the state of the system. Means if these terms are having a constant value, a fixed value, then the system will not change. It will be in a fixed condition, in a particular condition. That condition is called the state of a system. And these functions are called state functions or state variables, which are depending on the state of the system. Okay, these are thermodynamic functions or thermodynamic variables. Since they are depending on the state, that is why they are also called state function. There are two types of thermodynamic functions. One is called state function, another is called path function. Okay, the functions which will depend on the path through which a system has changed from a state A to state B are called path functions, if the functions depend on the path. And if the functions like pressure, volume, temperature, quantity, etc., number of moles, that is mass also, these functions are called state functions, as these functions depend on the state. So state can be defined as, state of a system can be defined as the condition of the system where the parameters are fixed, they have a certain value. Okay. Now the interesting thing is this: we no need to fix all these values at a time. If suppose out of these four, these are the primary state functions, the main state functions: pressure, volume, temperature, and the quantity or the number of moles or the mass, whatever you can say. Now, any three out of these four, if we fixed, then rest one will be automatically fixed. Means suppose any three of them in a, suppose a closed container, with a movable piston, in a cylinder a gas is taken. Okay, now suppose any three of these four are fixed, then automatically the fourth one will be fixed. For example, suppose it has a fixed pressure P1 and it has a fixed volume V1 and its temperature is T1, then the quantity will be fixed. Means if we change the quantity, then any one of them or all of these will change. Okay, let us take another one. Suppose the quantity is fixed here. The matter is neither coming out nor any matter is going inside. So number of moles, suppose 1 mole of any gas is kept. Okay, now its pressure is fixed, volume is fixed. If we change the temperature, if we increase or decrease the temperature, either the pressure will increase if this piston is fixed, or if the piston is movable, frictionless, movable piston, then the volume will increase. If we don't fix the piston, means if we don't fix the pressure. Okay, so these functions are called state functions. Okay, now another term, important term, is internal energy. What does it mean? What is internal energy? In simple sentence, we can say the internal energy is the total amount of energy present in a system or in any object. That is called internal energy. Internal energy will include all types of energy. For example, if a system is containing some heat energy, electrical energy, any other form of energy, mechanical or electrical or any other form of energy, the total amount of energy is called of the system is called internal energy. Internal energy is denoted by U. Now the thing is, internal energy of a system cannot be precisely calculated, the total internal energy. But interestingly, it is not required also. We need only the difference, change or the increase or decrease of internal energy. Suppose a system is in state A, and by giving energy or by doing some work, the system is changed from state A to state B. When it was at state A, its internal energy was UA, suppose, and in state B, its internal energy is state UB. So neither this UA nor this UB we can calculate accurately or precisely. But what we can do, we can find the difference. Suppose it is increased, then we can find the difference in internal energy. It is written as delta U, and this is required. This change in internal energy is required in thermodynamical calculations. Okay. Now, internal energy is a state function. Internal energy is a state function. How can we say that? State function means the functions which depend on the state of the system, not on the path of the system. If a system has moved from state A to state B, and suppose the system can be changed from state A to state B in two different ways, then at state A its internal energy is UA, at state B its internal energy is UB. Then whichever the path you follow, suppose this is path 1, this is path 2, when the system will reach from state A to state B, its internal energy will be UB. Whichever path you wish to follow doesn't matter. Okay. Now, how can we establish this fact? It was established by J.P. Joule in between 1840 to 1850. 1840 to 1850, that internal energy is a state function. Okay, now let us understand it with one example. Suppose a system is there and we are doing work on the system, a mechanical work. Okay, now work is done in two different ways. The first way is, suppose in a beaker, this is our system, in a beaker water is there, so it has a fixed value of temperature, it has a fixed value of volume, etc., and quantity obviously. Now if there are in two different ways we are doing some work in this system. Number one, by using a paddle we are doing a mechanical work. So by churning the water, the temperature will increase. Now the temperature is increased from TA to TB. So the difference in temperature is del T is equal to TB minus TA, and the change in internal energy delta U is UB minus UA. Okay, now in another way we are doing, suppose this was a mechanical work, now we are doing an electrical work using an immersion rod. We are increasing the temperature again from TA to TB. Now the temperature difference is again same, TB minus TA. Now since the temperature, same amount of heat is increased, there will be the value of delta U will be same, delta U will be UB minus UA. Now see, two different paths are used but equivalent amount of work is done in two different ways, but the increase in internal energy is same. The increase in internal energy is same. What does it mean? It means it is showing that the internal energy is a state function. It is depending on the state of the system. It does not depend on the path of the system, because we are following two different paths, but the increase in internal energy is same. This fact was established by J.P. Joule to prove that internal energy is a state function. Now in place of work, suppose by supplying heat we are changing the state from state A to B of the system. Okay, now suppose Q quantity of heat is absorbed by the system to increase the temperature from TA to TB. So the internal energy was UA and it is changed into UB. So change in internal energy, again delta U will be UB minus UA. Okay, now the same amount of heat is removed, then it will be found that the change in internal energy is minus del U. Means the sign is just opposite. The signs are opposite, but their magnitudes are same. Okay, so the same amount of heat will be absorbed in the first step, and that same quantity of heat will be removed or radiated by the system. Okay, so this way also it can be established that internal energy is a state function. So we have seen that by doing work, internal energy can be changed, increased or decreased. By supplying heat, internal energy can be changed by increased or decreased. Okay, now let us consider the general case where both the things are done. So in change in internal energy is actually the combination of the heat and work done. Okay, this is the mathematical expression for the first law of thermodynamics. Okay, delta U is equal to Q plus W. Let us understand the sign convention. If the work is done on the system, then the work will be positive. The sign will be positive. If the heat is supplied to the system, then the sign will be positive. Okay. Now if the work is done by the system, then the work will be negative, and the sign of Q will be negative if heat or energy is removed from the system. So increase in internal energy is equal to the amount of energy, amount of heat supplied to the system and the work done on the system. Now let us see the work done in thermodynamics. Mainly here, work done means we will consider the mechanical work. Mechanical work and specifically pressure volume work. Pressure volume work. Okay. So let us understand first the system. The system is like this. It is a cylinder where a piston is attached, and the piston we are considering as frictionless piston. The piston is frictionless, means if it moves, if it goes up or down, it does not create any friction, and that's why no energy is lost. Now a gas is taken inside this cylinder. Okay. Its pressure is, we are considering it as P internal, and atmosphere is having one pressure that is considered as P external. Okay. Now suppose the volume of the gas, initial volume of the gas is VI. Okay. Now suppose the internal pressure is slightly more than external pressure. If the internal pressure is slightly more than external pressure, then what will happen? The piston will move up. Okay. Now its final position is here. Okay. Now let us consider the length is increased, L. The length of the piston increased by L unit, and the cross section of the piston is A. Okay. Now let us see. As we know, work done is equal to force into displacement in the direction of displacement in the direction of the force. Okay. So again, what is the relation between force and pressure? P is equal to, means pressure is equal to force per unit area. So we can replace the F by P into A. So P into A into L. Into L is the length. Okay. Now L1 was the total length, suppose, and the final length is L2. So L2 is bigger than L1. So this is the increase in length. So the increase in length we can write as delta L. So A into delta in L means the increase in volume. So we can write here delta V. So simply we can write P delta V is the work done by the system. Work done by the system. As the gas expands, the work is done